Our goal was to create a low-cost vein finder for patients with invisible or rolling veins, with the hope of making the procedure of blood drawing more efficient and in turn causing less pain for the patients.
This is an example of somebody with spider veins.
This is a patient with veins that are hard to find.
For patients such as these, drawing blood can be extremely uncomfortable, and it can often take several pricks before it can be done successfully. Prior to construction, we had to research the following.
Originally, we had planned on spending $60. However, with the aid of grants and donations, we ended up spending around $33.
Thank you to OKW Enclosures Incorporated for their generous donation of our plastic enclosure.
Shout out to our local Radio Shack for hooking us up with some of the supplies we use, such as soldering wire, circuit board, and a switch.
This is our plastic enclosure that was donated, which we eventually cut holes in for our lighting.
We cut a piece of circuit board to fit in our enclosure, which we then screwed in.
We then cut a hole in the circuit board to be used for the location of the LED lights.
We staggered the LED lights on both sides of the hole.
This is the setup of our LED lights and resistors prior to soldering them into place.
Our original soldering gun proved to be inefficient in the tedious task of soldering our wires together.
This is how the first soldering gun made me feel. We appreciate the donation of this professional soldering gun from Southern Petroleum Laboratories. We placed the LED lights in the circuit board with the positive end facing the inside of the hole, which we soldered to the existing wire.
Here are the lights in place before soldering them to the wire. Now here's a live video of Shelby soldering the lights.
By using a battery checker, we tested which end of the LED lights was positive and learned that it was the longer end of the LED lights. So we soldered all of those onto the existing wire to create a circuit.
Next, we soldered the left end of the resistor to the negative end of the LED lights and cut off the remaining wire.
This is the front of the circuit board, about halfway through soldering all the lights and resistors together.
Our vein finder works by using infrared LEDs. When we shine the lights on the flesh, the veins are illuminated. This works because the veins absorb more of the spectrum of light than the surrounding tissue, causing them to appear as dark bands. This is similar to the effect of shining a flashlight under one's hand. Originally, the spectrum of light was too broad to illuminate the veins, but once we added this friendly plastic, the range of light was centralized, revealing the veins as dark bands.
As you can see, our product is small and easy to use. Although the dark veins are not visible through the camera, they are easily seen by the technician in the rectangle hole.
Companies such as AccuVein have produced a similar product to ours, but because this product is so advanced, there are multiple theories on how it works. Some say that it works by using an infrared camera and an LED projector that projects the image back on the skin. Another idea is that the product uses a laser that responds to the hemoglobin in the blood, making the veins stand out. However, these products can cost nearly $5,000, while ours costs a mere $33,000.
One of our biggest setbacks was figuring out the wiring and the relationships between the resistors and the LED lights, which we had to do research in order to uncover.
By contacting GiveBlood.org, we were able to introduce our vein illuminator to the medical field with the hope that it'll one day help many patients. A big thanks to our mentor, Mr. Rowland, for his knowledge and his patience in our project.